My name is Ole Van Aallen, and I represent you the Williams materials model and why it is important to include materials in an integrated assessment model. So first, I'd like to start with why it is important to integrate materials in the integrated assessment model, like William, then the methodology that we applied in the materials model. Then I will show you some partial results that we obtained with William. And if there's time left, I would like to show you how to navigate the materials in the Venza model. So what are the trends that we see regarding the material consumption? Wealth creation is like tightly coupled to the conversion of resources and materials, and growth means extraction of more resources like metals and other materials, energy, crops and woods from forest, and we do mine the ecosystem on land and water, and we also need human labor. We can see, like when we look at the trends, that a GDP per capita is usually correlating quite well with like the material footprint per capita in tons, and this material footprint compromises all materials that we extract from the earth. And we can see similar trends when we look into the global energy consumption based on primary energy consumption. And in absolute terms, like the fossil fuels, which you see here in black and yellow and red, is still rising. And the new energy demand that is coming is only the new energy demand is fulfilled by the capacity built by renewables and hydropower and nuclear, but in absolute terms, like fossil fuels are not declining yet. So we needed to integrate this aspect also in the availability from fossil fuels into the integrated assessment model. When we look at metals, we can see similar trends, like all metals, metal extractions are rising. So nickel demand and demand for other metals is expected to rise. This is due to the coming demand from steel, but also due to the new energy technologies when we want to shift to renewables. And similar trends we can see in copper, like copper demand is rising and copper extraction is rising. Same goes for steel, and the same goes for aluminium. So we needed to include all these materials to see, are they available? Are we limited by their availability? And what effect do the prices have on the economy? So here you can see a chart where you can see what kind of amounts of metals were mined in the year 2021. And we can see the majority of metal that we use in our society is iron ore, which gets made to steel and is used in a lot of different kind of purposes, but mainly in construction. And here we can see also the industrial metals like copper, aluminium are also in high demand, like aluminium nearly 70 million tons, like 86 million tons, and copper 21 million tons. And the technology metals are also on the rise on extraction because of because of GDP growth, population growth, and the widespread of new technologies like technologies like phones, mobile phones, and computers, but also the renewable energy technologies. So here we can see what the metals are used for mainly in society. I took only two examples. We can see that steel is mainly going into building infrastructure and mechanical equipment. Copper is used for power generation, distribution, and transmission, and also in construction a lot. But when we think about materials, we face several problems. One is that we have a declining ore grade. I don't know if you're familiar with the term ore grade, but if you think about the body of rock that contains copper, the amount of copper that is contained within this original rock before we make refined copper of it is declining. And this is a trend that we can observe for copper, but we can also observe it for manganese, chromium, nickel, iron, and for several other metals. What does that mean? That means that the energy consumption associated with the mining and refining will rise because we need to extract more raw material, like more ore body to get the same amount of refined material that we can use in the technologies that we want to dispatch or want to use in the society. So as I said, the relevance of our metal or like our materials in society, especially for metals, become really evident. Like we have, of course, already a high demand to sustain the society that we have. But here's a chart showing that if we compare, for example, a conventional car with an electric car, it is more material intense and requires more materials, especially when you look at copper, the ocean blue bar. And the same goes for the power generation grid. There we can see that the offshore wind and the onshore wind and solar PV require more than natural gas or coal plant. So like we expect with the transition, that the demand for materials will rise even further, and the demand for materials will rise anyway due to population growth and growth of GDP, and therefore growth of affluence and higher consumption of materials. So there's two reasons why we will see like increase in demand in general. So the same goes for fossil fuels. Fossil fuels are still relevant. You might ask why we would model fossil fuels in a model where we want to model the energy transition, but 80% of our primary energy consumption is still based on fossil fuels. And here you can see a nice illustration how much we actually consume in comparison to the Burj Khalifa in Dubai. And the relevance is obvious because we have like historical ties. Our infrastructure is built to accommodate and use fossil fuels. This is also like like really relevant sector. So it's relevant for the GDP growth and job creation. There's a lot of like industry in place already. So we need to replace this. It is a reliable source of energy as long there's fossil fuels available, because we don't have like the issues with intermittency or storage, and it's weather independent supply. It is a transition enabler, so we will need fossil fuels for a while to enable the transition, because we need the fossil fuels to mine the metals in the materials and sustain the system as it is to build up the renewable energy infrastructure. And yeah, we are really dependent on the technology. Some sectors are already discussing how to switch away from it, but many relevant sectors for society depend still on fossil fuels. We need to also build a efficient storage grid, as Lucas mentioned in the presentation earlier, and all together it is also political pressure can be executed with fossil fuels. And this shift requires time. So like we will see like quite a while that fossil fuels will remain relevant in our energy system until we made the transition, because the transition is not happening from one day to the next day. So now I would like to explain you a little bit the methodology of the Williams materials model. You probably saw this graph several times now during the last 2 days, but so this is the William model, and the materials model is here, located here. And our motivation was that materials are crucial for the economic and social progress and for the energy shift. So we wanted to include this parameters or these kind of limitations. A limited number of integrated assessment models consider this aspect. So for many, it's an exogenous variable that is feed into the model, but we wanted to model the availability, the price, and the dynamics that it creates. And we wanted to enhance also the Medeas approach. As you probably heard, that William is like a continued version of Medeas, where we got only scarcity alerts when we use too much material, but this time we wanted to also integrate a price signal that is able to have an effect on the economy if there's scarcity in material availability. Yeah, and then with that, we explored the scarcity impacts of the economy and energy. And we wanted to integrate the materials and fuels, which are like physical terms, with an economic multi-regional input-output model, which is monetary terms. And the goal was therefore to address the biophysical limitations that we have, because not everything is there to the extent as we might want to consume it. The methodology is based on cost loop diagramming the relations and understanding the system, and then translating it into a system dynamic model where we applied mass balance equations, and the flow of materials goes from the geological source to the markets via exploration and processing. And then we also track what is traded, sold, and what is used in the society. And in the case of metals, we look also at the quantities that are lost in society or re-entering the market due to recycling, and look at the quantities that are recycled. So now I would like to show you where we are in the materials model and what is modeled actually in the materials model. The materials model consists of the four base metals, which are copper, iron, aluminium, nickel, and these are linked with the multi-regional input-output model of the economy. Then we have modeled the crude oil, natural gas, and coal. And we have also modeled uranium. And then we have modeled several metals that are relevant for the green energy technologies. The model is linked to the energy model and to the economy model. So the economy model is sending the economic output by sector to the energy model and also transport economic demand to the energy model. The energy model decides or like calculates the transport final energy consumption and reports that to the economy model. The economy model gives economic output by sector, and here's also the sectors of refining, mining, and recycling copper, iron, aluminium, and nickel to the materials model. And we send from the materials model the metal prices and the prices for the fossil fuels. The energy model is asking for materials for the renewable energy technologies. It sends like the demand from primary energy commodities, so like for crude oil, natural gas, and coal. It asks for the demanded materials for the electric storage capacity. And it also asks for the materials required for the electric vehicle batteries. And the materials model reports like the embodied energy in materials. So when you think about the graph, if we dig into lower qualities of ore, then the material intensity of the mining and refining process is increasing, and that is reported to the energy model. So the feedbacks in a simplified way basically work like this. When we look at the metals, we have like the economic activity in 62 sectors across 35 regions, and that creates a metal demand. Then the metal models compute the extraction of materials, how much is recycled, how much is lost in society, and the price of the material. And the price is then, like linked back to the economic model, which in the next time step is calculating the new economic activity. Similar is a link for economy, energy, and hydrocarbons, but here we have like the economic activity, which creates the final energy demand. And then in the energy model, we calculate in the energy transformation chain how the energy is produced, and that creates a primary energy demand, which is then linked to the hydrocarbon model that calculates the extraction and investment in infrastructure for extraction in the hydrocarbon model, so in the crude oil, natural gas, and coal model. And the prices then are linked back to the economy model. And this is also a loop which is like taking place every time step. This create like to the question of the last presentation, for example, this creates also the fluctuations in the price, because depending on the tension between supply and demand and how the economic model reacts on the newly calculated price, you will have different outcomes of the final energy demand. So then I would like to start with an example. How did we model it? How are these models functioning? And this is copper as an example, but the aluminium and the iron and the nickel model function quite similarly. So we start with the resources, and resources become reserves over time via prospecting. And also in some models, this is a price-dependent variable. Then we have also secondary mining taking place, because not in all cases, like iron is, for example, mainly primary mined, but copper is also mined from other mining operations like gold, for example, in the standard side product. So we trace this and the availability of copper. This goes into the variable like the totally mined per year in million tons per year. And this is entering then the market stock, where some of the market or like some of the sold material is already new scrap because it is not entering the in-use stock. It's recycled during the production process. What is sold to the market is decided by the demand coming from the economy model in the red variable. And then we trace like how much copper or material like is independent. It's also the same for the other materials, is currently in use and how much is going out of use and leaving to be disposed. And then we lose, of course, some of this material because some of the material is lost during processing or improper recycling or it's not disposed correctly. But some material is also recycled. And this is depending on the end-of-life recycling rate. And there we have two options for the user. It can be either like a variable that is dependent on price, that we track the price development and the recycling rate development, or we can give the user the opportunity to set the end-of-life recycling rate. And this is also flowing back into the mining flow that is going to the market. Then the model or the mining in general is profit-driven. So the higher the profit, the more mining will take place. And the profit is determined by the cost of the mining operation and by the mining income. The costs is like a function where you have to imagine these are arid variables. They are like in 6 layers. So we have different ore qualities, and depending on which ore qualities is mined, a minimum price is required to extract these to make it possible. And the mining income is, of course, determined by the amount that we mine and the current price that we calculate. And the price is calculated based on the tension between supply and demand, but also depending on the ore quality. So with higher quality of ore, we have a lower price and vice versa. So these prices are then delivered to the economy model. And we also track the energy required for mining and refining. So with higher quality of ore, lower energy requirements, because of course have. And this is of course dependent on the amount that is mined and from which kind of ore body this is mined. So what is covered, or how are the fossil fuel models modeled? We have there 3 compartments, like the extraction. This is like now on the example of oil, but it is similar to coal and gas. So we have extraction of oil, gas and coal, supply and demand, and the price and the infrastructure. So the extraction infrastructure. So here we have a similar structure as before. We have like the resources, which become like prospected and then move to reserves. The oil gets extracted, or gas or coal, and then we track what is totally extracted just to have an overview to compare it to literature data, and also the assumption of ultimately recoverable resources. So like we just trace that, and this variable will play a role later, and I will explain when we come to the yellow column why. So, and then we have the supply and demand and price of oil. Here we have the primary energy or primary commodity demand coming from the energy model. And then we made an assumption about the average capacity per well per year, which is the simplification of the real world. Because in reality, like oil wells have like really high productivity or really low productivity, but you can decide either to like it was very difficult to decide how to capture this because there's so many wells active. So we built a average capacity per well, and then we calculate the total extraction capacity, which is based on the average capacity per well and the number of wells that are currently extracting. And this flows into the variable where we calculate the spare capacity, and which is like the tension between supply and demand. And with high spare capacity, we have lower prices. And with low spare capacity, we get higher prices. And this is calibrated to the historical prices. And this estimated price is then sent to the economy model. And the estimated price is also deciding how much we should invest in new extraction infrastructure. So with higher prices, we invest more in extraction infrastructure. With lower prices, we don't, or we invest less. And here we have the desired capacity. So like the desired capacity based on the price. but we also have a maximum investment capacity because you can like basically the price could shoot up really, really high, and then the model wants to build infinitive amounts of wells, but that is not physically possible. So we looked at historical data that looked at the maximum increase from one to the next year to give it like a physical limitation in that sense. So here's then the deciding factor if we take the desired capacity or the maximum capacity. And this flows into the investment in wells, and then we have like the stock of active wells, which is used to calculate this total extraction capacity. But we also have a depletion of wells and or extraction capacity in coal. It's mines, of course, and the depletion is depending on how far we dig into the ultimately recoverable resources. So our assumption is the more or the lower this one is, or when we reached over half, then the depletion of the wells is increasing, because we argue that you would dig first into the giant fields and the giant and easy extractable oil fields in the case of oil, but then you would have like more like fracking and other forms of oil extraction, which are having not such a long run time, so they deplete faster and need to be replaced quicker. We also modeled uranium. Uranium is modeled with the Hubert curve and like a depletion curve. So we have historical data about the depletion curve and made a maximum extraction curve. So until we have this amount of resources available, we can supply each year a certain amount of exajoule per year, which is declining when the resource stock is declining. Then we also have several materials that are required for the green energy technologies. So here we focus on the green energy technologies, solar, wind, and batteries, because they're really like, or they depend on a lot of different metals. And we wanted to trace, like, is there enough metals available to build these capacities? And then we analyzed different specific tech variants like mono C, poly C, and different battery types as well. And we reviewed the material intensity in kilogram per megawatt for 24 materials, including cobalt and lithium, and compared the mineral demand versus the geological availability for 24 metals. Yeah, and the metal submodels offer then a risk assessment for future metal supply. These are not linked to the economic model. This is due to the structure of the economic data in the input-output table, because there you find, like, for example, the sector other metals or ferrous metals, and then you would have to disaggregate these for like 10 or 15 different metals and then calculate the demand for these metals, and which is incredibly difficult. So we had to find a different approach to solve this, to integrate these metals as well. Now I would like to show you some exemplary results, and we carried out different studies here. I will start with an example that we carried out on the oil model. We did 3 case studies. One case study where we looked into the different resource estimates, because there's a lot of discussion in the literature about how much resources are available. And yeah, we wanted to see how sensitive is the model to these kind of variations in resource availability. Then we looked, like we modeled the OPEC's varying spare capacity levels. So the OPEC countries, you're probably aware, have like a lot of the extraction capacity of fossil fuels, especially oil. And we wanted to look into the relations between the energy and economic and materials model. What kind of effects does it have when the OPEC countries decide to flood the market or take capacity away from the market? And then we also modeled something similar to lockdown situation to see if the model is also able to model short-term effects like the COVID pandemic lockdown. And the objective was to demonstrate the interlinkages and the advantages that come with a fully integrated model between the economic and energy and materials models, and also how this price feedback helps to be an example how you can model scarcity and limitations, biophysical limitations. In the studies, we excluded other WILIAM models like the climate impacts and also in this case, we excluded the metal models, just like purely focused on the oil feedback. And also we excluded potential technology improvements, like Lucas explained earlier. With higher oil prices, we would also probably trigger a shift to more renewable technology. But we just assumed that the economy will stay as it is and switched off these feedbacks. And yeah, what are the key effects that we can observe? It alters the household expenditure on various transport modes and decrease disposable income for other non-durable goods and reduces the overall real-term expenditure. So let's go into the first case study. See, you can see the oil endowments in the literature. We looked into different reports, like from official agencies, but also from well-known researchers that research the field of oil, like Lahere and more, and looked at the lowest values that we could find, the medium values and the high values, and use this as as the input for the model and to see how it reacts. So I will show you what happens. Let's start with the graph on the left. So we have here the gross domestic product real. And here you can see the GDP index and then the years on the x-axis. We have here, like the red line is when the economic model is not constrained by the material model. So there's no price feedback of the materials model. So there's no limitations to how much can be consumed and the price is not rising. And we can see in this in this scenario, like the economy would grow quite high, like the GDP would grow quite high, and in this scenario we would extract more oil than is actually available, even under the highest estimations, assuming that the economy stays in the current state without switching to renewables even more. But here we can see clearly when we switch on the full feedback and have the price effects that we see like a different behavior, because there's limitations, biophysical limitations, which are then transferred into economical units by sending the price signal to the economic model. The black line is like the high resource scenario, the blue line is the medium resource scenario, and the green line is the low resource scenario. And there we can see in the low and in the medium resource scenario, we can see like a decline of GDP, because the economy remains reliant on oil because we don't switch to the renewables, and then the prices become so high that they constrain the economy. And the prices become basically so high because the availability of oil is not given, which you will see in the next slide. Then we also looked at something else. We looked at the effect on oil availability, where we used the medium resource scenario, and can clearly see that oil importing nations like the European 27 and USMC are really negatively affected in the moment when the prices rise. That is here when you see the GDP declining, while like other regions that are major oil producing regions, so the rest of the world is also containing the OPEC countries or Russia, which are major oil producers but not major oil consumers, they are not so affected by these rising prices. So what we can see also in the first case study is like in the high scenario, this is here in gigabarrels. We have like in 2005 quite a bit left. In even in the end of the century, we would have still oil left, but in the medium and low scenario here should actually be a little bar, but it is so marginal that it's not visible. We have nearly no oil left. So is it really smart to rely on this dependency or use up all the oil for the uses that we have currently? It would be probably smarter to save some and have some in the ground also for other applications. Here we can also see when the GDP peaks, and this is closely linked to the peak in oil. So it's not only important to reduce our dependency on oil in terms of environmental reasons, but also we have to decrease the dependency of our economic system to prevent like an economic decline. So then we modeled the effect of the OPEC countries when they would reduce the spare capacity or increase the spare capacity, which is like this is the OPEC plus countries, and there we observed like the historical behavior of the OPEC and the spare capacities withhold and the correlation with the oil price. And then we modeled a scenario where we said basically in the beginning they had 3 million barrels spare capacity per day. And in one scenario, they had zero spare capacity. In one scenario, they had high spare capacity. And here you can see the full feedback. So like this has an effect on the oil price. Of course, when the OPEC is withholding a high spare capacity, then the prices of oil is rising. Vice versa, it's declining if they don't hold spare capacity. And that has also an effect on the GDP as well. Here we modeled the effect of like a lockdown. So you can see like in the demand for oil, no lockdown scenario, the demand would just be continuously rising over the years. While in the lockdown scenario, we see like we reduce the need for personal passenger transport by 20%. And then we see also a decline, which is like a variable that we affected in the economic model. And then we see a decline in the oil demand and also a decline in the oil price, which is then rebounding after we lift the lockdown restrictions. So here are some policy recommendations. I will not go into detail because I think, I don't know what time. Oh, I used already quite a bit of time. So I will say just is we could say that we need to switch really fast from fossil fuels away because also there's limitations to the availability. And what we would also like to encourage is like improve the data and yeah, strengthen like resource capacities to prevent, for example, disruptions when you have like release or withhold of spare capacity, or you have situations like not availability of gas, like Russian gas. So we need to plan for these kind of disruptions in our societies to make our societies less vulnerable. But then I would like to go into some examples of the metal models and what you can do with them. I will jump this. So what we basically did is like we modified the end of life recycling rate, where we had like the end of life recycling rate in the copper model set to the normal correlation between price and recycling rate development. And here we increased the recycling end of life recycling rate to 60% and here to 80%. And that had, of course, an effect on the price because we had more material coming from recycling and the extraction lowered according like in the same structure as you would assume. And another reason why the price is affected is because we were not or we didn't have to dig as early into lower ore qualities as if we would run with the baseline scenario, for example. So this is like one of the things that you can analyze with the metal models. Then I would like to go a little bit on the demand for green energy technologies. So we have the materials that are also modeled in that aspect, where we traced like the mineral intensity of different transition technologies in kilograms per megawatt, and covered our solar PV with 4 sub-technologies and wind onshore, offshore, and also battery sub-technologies. We looked into transport technology. So I will present you like a scenario where we had 4 different kinds of scenarios how like future transportation could evolve. And first we looked into the different kind of battery technologies and what kind of material requirements they have. They don't all require critical materials like nickel and cobalt, but then they have other downturns, like they are maybe too heavy to be used in a 4-wheel normal passenger car. Here's also the study that you can find that is carried out, and there's more detail to this. And then we developed like a scenario with expected trends of electric vehicle transport, which is the business as usual scenario. Then we have electric vehicle transport scenario with like a high penetration. So a very high fleet of personal passenger 4-wheel transport. So replacing basically combustion engine cars with electric vehicle cars. And then we have also a scenario with e-bike and light vehicles, and a degrowth scenario where we have like e-bikes and reduction in total transport demand, especially air transport. Also, additionally, we modified here the end-of-life recycling rates to 85%. And in the other business as usual scenario, we looked at or we used the current recycling rates. What we can see is like that these different scenarios require different terawatts, which is also equivalent to different material demands linked to it. Accordingly. So like the high is of course trending the highest when we replace all combustion engine cars with all electric vehicle or like only electric vehicle cars, we will have a capacity or a high need for capacity increase in terawatt, and that means a lot of material required. And like the degrowth scenario, for example, is scoring the lowest terawatt requirements. And then we looked at the cumulated primary material demand until 2050 under the different scenarios and compared it to the reserves. So you can see here that this is the scale for the reserves, like how much percentage of the reserves would be used until then. And we can see clearly that and then we can also see the orange is referring to the rest of the economy, and in the blue is referring to electric vehicles. And we can clearly see that here, for example, some materials are not becoming scarce or not in danger to become scarce, because here with aluminium we have maybe 12% or between 12 and 14% of the reserves. But when we look at copper and look at the different EV trends, we can see that the rest of the economy is already demanding a lot, but in the EV high trend, we can see like 35% of the copper reserves that are known would be used up only by the electric vehicle high trend. And we did this also for cobalt and lithium, but this you can find also in the published paper that was linked on the PowerPoint slide. And here we have also done this for manganese, nickel, and graphite. And here you can see like nickel, even in the like not considering the electric vehicle battery demand is already under pressure with like normal demand with the rest of the economy. So now you might think recycling might be the opportunity to solve this problem, but we have the end-of-life recycling rates set as a target pretty high here, but we can see these end-of-life recycling rates are not met, even though we set them really high. And why is this? It's of course because the material is locked up in use and we still have increasing demand in the same time. So we have an increase in demand over the whole period, while a lot of the material that is entering the use now will be locked in use for the next 50, 60 years, depending on the material. So very high recycling content is not the short-term solution, and what we have to do is increase mining. Yeah, here's the conclusion. I summarized that already, that we have like, that we can see different pressures on different materials depending on the scenarios. So for example, transportation transition scenario based on vehicle shift to electric vehicles with the private four-wheeler model face risk in mineral availability for copper, cobalt, nickel, manganese, and lithium. And some minerals demand is driven by the rest of the economy and already face like problems like copper, manganese, and nickel. And the switch to electric vehicles is like really, and auxiliary infrastructure is really material intensive. So yeah, the diversity in the sub-technologies helps a little bit to alleviate the pressure, but not totally, because most of them still require copper, for example. Yeah, what is the advantage of doing this approach that we have, like this like fully integrated approach? Like I think the advantage is really that we can trace what is happening when we have like limitations of material supply, and you cannot just dream about like certain kind of renewable capacity, because you first have to check with the biophysical reality, is this material really available to sustain this infrastructure or to build this infrastructure? Also, it is good that we have a modular and open source approach, because if you're interested in certain materials, you can also take only certain materials out of the model and just do research with them, or you do research with them in combination with the economy or with the energy model. And yeah, we can prove with these case studies that the linkages between supply and demand and tension in the availability is really working and has a full effect. And it is in comparison to other models where you often work with supply cost curves or with exogenous prices or availability, or like unlimited availability of resources, you are more able to give a more comprehensive picture of the reality. Yeah, I would like to thank you here and close.